Okay, now we will take a look at how do we evaluate the bias to see whether it's significant, and even if significant, we want to do another step. The next step is that we have to check whether the amount of bias is too much or not. Okay, if it's too much, we will not accept that accuracy. But if the amount of bias is small, okay, we will accept it. Okay, and then we will allow our measurement system to have a little bit bias. Okay, and to evaluate the bias, okay, we will take a look at the method for bias appraisal. Okay, first, we have to have a master part. Okay, a master part means a workpiece, okay, that we assume that we know the correct value of that part. For example, okay, if we appraise for the length of the part, okay, so we will have a master part, okay, which was measured before by an accurate measurement device, okay, and if that accurate measurement device, okay, told that that part has the length of, for example, 10.0 centimeter, okay, we will believe that that master part has what we call master value or reference value or true value of 10.0, okay, and to get the accurate gauge or accurate device, okay, we have that gauge, okay, is the one, okay, that is kept in a good condition, okay. It will be at, okay, maybe an organization or institute that correct or take care of a device in good condition. For example, in Thailand, we have สถาบันมาตรวิทยา okay, which is an organization that carry a lot of measurement device in good condition, okay, and then if, okay, our company, okay, take one part to สถาบันมาตรวิทยา, okay, and have that part measured by a gauge, okay, that we believe that it will give the correct result, okay, and then if it gives the number which is 10.0, okay, we will believe that that part has a dimension of 10.0, and that value is called master value, okay, and that part we will call it a master part, okay, or a part that we believe that we know is true value, okay, and then we will take that part back to our factory, okay, and then now if we want to evaluate the accuracy of our current gauge or the grade or any gauge that we want to appraise for accuracy, okay, we will do the third step, okay. The third step is to measure that same part. That means we will measure that master part again, okay, with the gauge being appraised, okay, for 10 times, okay. So 10 times is called repeatability, oh sorry, replication in this case. That means we will measure the same part for 10 times, 10 replication, okay, and then we will calculate in an average, okay, of the observed value, an average of the 10 values, okay, here that we have. And next step, number 5, we will calculate the bias, which is the difference between the average of the observed value and the master value, okay. Now we will get the amount of bias, right, okay. And next we will do the 6th step, which is we will do hypothesis testing, okay, using t-tests to conclude that whether the bias is significant or not, okay. If it's significant, okay, statistically significant, okay, we will believe that bias occur, okay, in our measurement system, okay? And if bias is not significant, okay, even though it has some value, but it's not significant in terms of statistics, okay, we will believe that our measurement system has no bias, okay, that is great, okay? And come back. In the situation that bias is significant, we will do the further step, which is number 7, okay, that we will perform further analysis to see whether the magnitude of the bias is acceptable or not, okay? To do so, we will do, okay, I will skip, okay, to this slide, okay, to see if the amount of bias is significant or is too large, okay? So we will compare the amount of bias with 2 things. The first thing, we will compare it with the process variation. Remember, we have learned about process capability analysis, right? Okay, suppose we calculate CP, okay, by comparing the tolerance with the process variation, which is quantified by 6 times sigma, right? Okay, 6 sigma of the process is called process variation, okay? So we can use the number from process capability analysis about sigma of our system, okay, of the parts, and then, okay, we will multiply it by 6, okay, to get the variation of the parts. So sigma here, okay, is calculated from the dimension of many parts, okay, different parts that we have produced, okay, and then we will compare the amount of bias, which is the upper part here, okay, with the process variation, and turn it into percentage, okay, and then we will compare the percentage with the criteria for acceptance. Okay, for example, if the percentage of bias over process variation is less than 5%, okay, generally, okay, we will accept that the amount of bias is pretty small, okay, and we can accept it. And in many industry, okay, if bias is at least 10%, okay, we will believe that this amount of bias is too much, okay, and we will not accept this amount of bias. Okay, between 5 to 10% is in the middle, okay, we may accept or unaccept it, okay, it depends on whether we're gonna, how much accuracy that we need, okay. If we need high accuracy, we will use 5%, but if we can tolerate some inaccuracy, so we will use 10%. Okay, it depends. So to be easy, you can design whether you're gonna use 5% as the criteria or use 10%. Okay, and if less than that, accept it. If greater than that, we will not accept that amount of bias. Okay, and that is the first indicator. The second indicator to compare the bias, okay, is to compare it with the tolerance of the parts. Okay, so suppose we measure the length of the part, okay, and it has the target of 10.0, and the specification limit is from 9.9 to 10.1. Okay, so the tolerance is 10.1 subtract by 9.9, right, which is 0.2. Okay, so 0.2 will be tolerance. Okay, and then we will compare the amount of bias with this tolerance value. Okay, and we will use the same criteria, okay, to accept this indicator also. Okay, so we can calculate 2 indicators, but to judge whether we will accept the amount of bias or not, we will focus on only the first indicator, which is to compare the bias with the process variation. Okay, and the second indicator just to inform us, okay, about the amount of bias compared to the tolerance, but we will not use it as the indicator to design whether we're going to accept the amount of bias or not. Okay, so to make decision, we will base on the first indicator, because we will pay attention to process variation, because the process variation is what we want to measure, right? Okay, so we do not want to measure the tolerance. Okay, so when we want to measure the process variation, we have to make sure that the amount of bias is not that much compared to what we are going to measure. That is why we have to focus on the first indicator. Okay, so if the first indicator, we pass the first indicator, for example, the criteria is 5%. If the criteria is 5%, if the bias to process variation is 3%, so we will accept the accuracy of the system, even though if the percentage of bias compared to the tolerance is greater than 5%, for example, is 8%, okay, we will accept this measurement system anyway, because the bias to process variation is only 3%, okay, which is less than 5%, okay. But if the percentage of bias over the process variation is greater than 5%, whereas the bias over the tolerance is less than 5%, we will not accept that accuracy, okay, because we pay attention to the bias compared with the process variation. Okay, do you follow that? Okay, come back. Okay, come back to the step that we do hypothesis testing, okay, of the bias. Okay, before we move to calculate these two indicators, okay, we have to know first that bias is significant in terms of statistical significance. So that means we will do this hypothesis testing where H0, the null hypothesis, is the mean. Mean in this case is the mean of the measurements. For example, if you the mean of the length of the part that we have observed, okay, is equal to tau. Tau is the master value or the true value of that part, okay. So if mu is equal to tau, that's mean on average, okay, we get the number which is exactly equal to the true number of that part. That's mean there's no bias, right? In this case, okay, let me get the pen. Okay, so H0, okay, just a second. Sorry, what happened? Okay, let me get the pen one more time. So H0 also means that bias is equal to 0, because bias is equal to the average of the measurement subtract by the true value, right? Okay. And HA is bias is not equal to 0, okay, or that's mean bias is significant. Okay, so we have to remember the hypothesis that we are testing. Okay, and then, okay, we will perform the t-test. Okay, remember that we use t-test instead of z-test because our n, the number of data point, is equal to 10. Okay, when we do bias appraisal, we will measure the part for 10 times. That means our sample size or the number of data points that we have is only 10, which is a small sample. Remember that when we have small sample, when n is less than 30, we will concern that this is a small sample, and then we will use t-test, okay, to test whether the mean is equal to tau or not. Okay, and to summarize, if you remember hypothesis testing, we will take a look at the p-value of the test, right? If the p-value is greater than alpha, significance level, remember that in statistics, usually we use 0.05 or 5%. If p-value is greater than alpha, okay, we will conclude that we will do not reject H0. And when we do not reject H0, that means we will believe in H0. That means we will believe that the bias is not significant. Okay, so you can remember, okay, in short, you can remember that you will do the t-test, right? And then you will look at, you will take a look at the p-value. And if the p-value is greater than 0.05, you will believe that bias is not statistically significant. But if the p-value is less than alpha, okay, the rules is that, we will reject H0. And when we reject H0, that means we will believe in H1. And H1 say bias is significant. Okay? So you can skip, okay, from this step to this step, that when p-value is less than alpha, you will conclude that bias is significant. Okay? And if the p-value is greater than alpha, you will believe that bias is not significant. Okay, this is the link, okay, or how do we use hypothesis testing to reach the conclusion about whether bias is significant or not. Okay. Okay, in a few minutes, we will do the workshop, okay, to make sure that you can do this. Okay, this is just the theory, okay, but in reality, we will use the software to calculate this for you, okay? So in theory, we will use t-test, right? T-test has this formula, okay, x bar is an average of the 10 times of the measurements, okay? And mu here, actually mu here is mu zero. Mu zero in this case is a true value, okay? So the t statistics compare the upper part is the bias, okay, with some what we call random error. This is, okay, a random error, which is sigma, okay, the standard deviation of the average, okay, of the average. And S here, okay, represents, okay, the sample standard deviation of the measurement. Okay, if you have to calculate it by hand, this one is, okay, use this formula. Remember that the formula to calculate standard deviation, and in this case it's 10 data points, okay, and you have 10 measurements here, okay, so you can use those 10 data points to calculate S, okay. So S is, so what does S represent in this case? Okay, you have to start your idea with that each X means the measurement of the same part, which is the muscle part, okay, but we measure it different times, okay. So the variation is what we call repeatability, or the variation in terms of regarding repeatability. That means the variation when we measure the same part but different times, that is called sigma regarding repeatability. Okay, so S here tells you about the variation regarding repeatability. Okay, it doesn't represent the variation of the parts, because in this case we measure only one part, which is the muscle part. Okay, and to judge whether the bias is significant or not. In statistical method, we have to compare it with a random error, okay? And then we will convert that amount to the t statistic, okay? The t statistic in this case, okay? And then if the amount of the t value is large, okay, that means the amount of bias compared to the random error is large also. I think we have lost the screen sharing, right? You can tell me if you do not see the slide, because when I talk, I will follow the slide. I'm sorry about that I just observed it right now. Okay, let me share the screen again.
ยังเห็นสไลด์อยู่ครับอาจารย์
ยังเห็นเหรอคะทำไมหน้าจออาจารย์มันหายไปล่ะเห็นอยู่นะคะขอบคุณค่ะเห็นอยู่เหรอ PowerPoint นะ
เห็นอยู่ครับ
โอเค good เนี่ยนะคะokay. And then okay, so if the amount of the t value is large, okay, when you have learned about statistic, right, from I'm not sure, in the second year, right, when t is large, and then okay, if is fall into the rejection region, okay, you will reject as 0, right? When the amount, the magnitude is large, okay, you will reject H0. That means you will believe that bias is significant. Okay, so this line is just want to remind you that we will use t-test to come up with the conclusion. Okay, but when you use it, it is very easy. You don't have to involve in this step, okay, because you will have the software to calculate, okay, the p-value for you. Okay, if you remember when you take statistics course, when you obtain the t-value here, you will convert it to a number, a corresponding number, which is called p-value, okay? And then you will compare this p-value with significance level that I have talked before, okay, to make conclusion. Okay, so we'll take a look at how do we do this, okay, in the workshop in a minute. Okay. Okay, we have talked about this. Okay, about this. Okay, so now we can do the workshop, okay? In this line, okay, I give you an example of the result from Minitab, okay, about the t-test, okay? So when we do the workshop today, we will get this exactly format of the results. Okay, we will do one sample t-test. In this case, they measure the weight. Okay, and this is the hypothesis that they were testing. Mu equal to this master part. Okay, this is H0. Okay, versus H1, which is mu, is not equal to this true value. Okay, so in Minitab, it won't write down H0 and H1 for you, but it will say test of mu equal to 100.3. So you have to know that this is the null hypothesis, and this is the alternative hypothesis. Okay. Okay, I will talk about this a little bit so that in the workshop you can practice it by yourself. Okay, so in Minitab, it will give you the result t-test like this. The variable in this case is the weight, okay, and the number of data points, 30, okay, and then it will calculate the x bar, an average of this 30 data points, okay, which is 100.917. So in Minitab, it will say that this is the mean, but you have to know that this is the sample mean. The sample mean, or the mean that is calculated from the sample, and we will call it as x bar. Okay. Okay. And the standard deviation, or S, okay, is calculated from this 30 data points also. Okay. And this is S. Okay. SE mean in this case is S over square root N. So it's equal to 0.587 divided by square root 30. Okay. And this is what we call sigma standard deviation of the random variable x bar, okay, where S is equal to standard deviation of x, okay, before we average it, okay. Each the x variable has the standard deviation of S, okay, but when we calculate an average, okay, that average is also a random variable. And then if we repeat this kind of experiment for the second round, third round, we will obtain another x bar values, and those x bar value is also a random variable which has this much standard deviation. Okay, I will not talk much about this, okay, because this is just the basic knowledge that you have learned from statistics course. Remember, like central limit theorem, okay, and this is related to central limit theorem, okay, but you don't have to pay much attention to that, okay. In the QC course, you can take, okay, that basic, okay, and then you can use Minitab, okay, or actually you can use Excel software also to do this for you. Okay, so what you need, okay, is what we call the p-value to make decision. And the p-value actually come from the t-value, okay, and the t-value here 5.75, okay. If I show you again, okay, one more time before we move to the application. So t comes from x bar minus tau divided by s over root n. Okay, so x bar is equal to 100.917. Tau is the numbers that we are testing in the hypothesis, or the true value, right? And then divided by s over root n, which is the standard deviation of the mean here. Okay, 0.107. Okay, when you calculate this number, you will obtain 5.75. Okay, this number. Okay. And then if you take this number and you convert it to the p-value number, it will be probability of the t statistics to be greater than 5.75, okay, plus probability that t is less than minus 575. This is the basic knowledge from statistics course, okay. You're testing two-sided. You have two-sided test, which mean the amount, the sign in H1 is not equal. So when you calculate the p-value, you have to have two terms, p greater than t greater than 5.75, and then plus the second term, which is t less than minus 0.75. And then when you calculate this number, you will get the amount which is very small. In this case, it's less than 0.0005. Okay, so I know that because I take a look at this value, the p-value, and it reported that the p-value is 0.000, right? Okay, but if you have knowledge, you will know that the p-value is the area, okay, under the normal curve, okay, and the curve is infinity, so it's not possible, okay, or it's impossible that p-value is exactly at 0. It cannot be 0, but it will be the number which is very small in this case. And because Minitab chose only 3 digits, okay, 3 digits, 1, 2, 3, okay, so we know that the last the fourth digit here okay, will be some number which is less than 5, okay, right? So that it will round down to 0.000, okay? If, for example, if p-value is equal to 0.0007, okay, so it will round up to 0.001, right? Okay, but in this case, p-value may be 0.0003, okay, so it will round down, okay, when it shows only 3 digits, it will shows only 0.000, okay. So in this case, I want to emphasize that, okay, when you do statistical analysis using Minitab software or Excel software, for example, and if it shows only 3 digits, okay, and if that number is 0.000, so when you report about the p-value, you should say that the p-value is less than 0.0005. You shouldn't say that p-value is equal to 0, okay? And then you will take this p-value and then compare it with alpha, which is 0.05, okay, to make decision. And in this case, p-value is less than alpha, right? So you will say, or you will conclude that bias is significant, okay? Or if you tell it in a long sentence, you will say that the bias is significantly different from 0. That means it has some number which is significant. Okay. And then you will compare that amount of bias with 2 indicators, right? So this is X bar, this is tau, right? So, or you can call it bias, right? And then you can compare it with 6 sigma of the part. And this number you have to get from process capability analysis, okay, that you have done before, okay? And you plug in the sigma value, okay, and then you get this much percentage, okay? And if you want to compare the bias with the tolerance, okay, tolerance here. So tolerance come from the difference between upper spec limit and the lower spec limit that you know, okay, from the parts. Okay, and then you get 8.4% here. Okay. And now if we use the criteria of acceptance of 10%, okay, so the conclusion will be that the first indicator, right, is 32.3% is greater than 10%, right? So you will not accept the accuracy of this measurement system, right? Okay. When you compare with the tolerance, it's less than 10%, okay? So the conclusion is that, remember that I told you before that when we make conclusion, we will use or we will consider only this indicator, and we will not use this indicator to make decision, but we just want to know, okay, for information. Okay, that's all. Okay, so come back to make decision. Okay, since this number or this indicator is greater than 10%, okay, so we will not accept the accuracy of the bias, or we can say that we do not accept the accuracy of the measurement system, or we will believe that the bias has the number which is too large. So we have to fix it, okay? So we have to go back and investigate the measurement system, what caused the bias. Is there something wrong with the gauge? Okay, or if there is something wrong with the measurement method, okay? So if we can find out, we can fix it, okay, to reduce the amount of bias, okay, in the future. Okay, so this is the whole process for doing bias appraisal. Okay, so up to now, do you have any question about the bias analysis? Okay, if not, okay, I will give a lecture a little bit more about stability and linearity. And after that, we will come back to do workshop, okay, to have you practice with Minitab, okay, about the bias and linearity appraisal. Okay. Next, we come to another analysis about the stability of the bias. Okay. In this analysis, okay, we will use control charts, okay, to help us to check whether the bias, okay, is changing over time or not. Okay, so remember control chart. Okay, the x-axis is the time axis, right? So this is the time, okay, period. Okay, for example, if we appraise the bias every week, so this is, you can plot two things, either an average of the measurements, okay, of the master part, okay. For example, this is the information from the first week. This is the second week, third week, okay, and so on, okay. And in each week, you will do bias appraisal, okay, and then you will get the average of the master values, right, which is X bar. If you turn it to bias, it's very easy, right? If you take an average and then subtract by the true value, you will get bias, right? And then you can plot the bias, okay, on the X bar chart, okay? And then you can see the variation or the change in the bias over time, okay? And then if you have a lot of data points, you can construct the control limits, right? And then you can use this control limits to judge whether the amount of bias, okay, over time is abnormal or not. Okay, like in the 4th, 5, 6, 7, 8, in the 8th week, okay, the amount of bias is greater than the upper control limit. Okay, so you will say that on average, the bias is at this level, right? At this center line level. But in the 8th week, we will believe that the amount of bias is abnormally high. Okay, so that means we have to investigate and fix this problem. Okay, in the first 7 weeks, the amount of bias is within the control limit. So we will believe that the amount of bias is stable at this level, okay. And if that level is acceptable, okay, so that means we can accept this amount of bias in the first 7 weeks. We don't have to do anything to fix the bias problem, okay, because it's normal, okay. And then we will take action only when we have the situation that the bias is greater than the control limits, okay. And also for the R charts tells you the variation, okay, of the 10 measurements of the same master part. Okay, so when we have the problem with the range, that means the repeatability is not acceptable. So X bar tells you about the amount of bias, where the range tells you about the amount of repeatability, okay. Okay, up to now, do you have any question about the stability appraisal? Okay, so you can apply control charts to do the appraisal about the stability of the bias, okay? And then you can use your previous knowledge about how do you construct the control charts, okay, to do bias or to do stability appraisal, okay. Next, the last analysis that we have to do with the bias is linearity appraisal. Okay, so in linearity appraisal, you will plot two things. Okay, the x-axis will be the measurement range. Okay, for example, your vernier can measure the part which is very small. Okay, from, for example, one millimeter to, okay, the big part, which is, for example, 10 centimeter, for example. Okay, or you can have any device, for example, voltmeter. Okay, the range can be from like 1 volt to 100 volt. Okay, for example. Okay, and then you want to see whether the bias, okay, is the same or is different when you measure the part which is small, has small value to large value. Okay, and if there is linear relationship, for example, in this graph, okay, you will see that when the part is small, the bias is small, right? And when the part is large, the bias amount is large also. So there will be a linear relationship between bias and the measurement value. Okay, so we have what we call linearity pattern happen. But if there is no relationship, your the graph will be like this, bias, and then this is the measurement values, or you can call reference values. The graph will be like this. Okay, when the reference value change, bias doesn't change. That means bias is constant over reference values. So that means when you measure the large part, okay, you will get the same amount of bias as small part. And if this amount of bias is acceptable, that means it's good, right? Because you can have acceptable value over the entire range of your measurement values. Okay, but if the bias has linear relationship with the measurement values, so you have to concern that whether the amount of bias at the large value, for example, large value is about like in this range, you have to test whether this amount of bias, okay, is acceptable or not, because it's large, right? You may be suspicious about that. Okay, so when the bias is changing over different values, so what you have to do is that first, okay, you have to take a look at each different values to check whether the bias is acceptable or not. Okay, if yes, you have to take a look at another value and then check whether it's acceptable or not. Okay, and then you do this for all different values, maybe a sample of different values, and then it may turn out that when the part is large, the amount of bias may not acceptable. Okay, so if that is the case, so you have to find a way to fix this problem. Okay, you may fix your gauge or measurement device, okay, or you can do what we call I will talk about this a little bit later, okay, but at this point, okay, I want you to know that if there is a linear relationship, okay, so you have to concern, okay, about whether you're going to accept the amount of bias for some reference value which may cause the bias up to the range that is unacceptable. Okay. So what we do is that we will take the data, okay, from, okay, different reference value, okay, and then we will calculate X bar for each reference value or what we call master value, right? So we will have 1, 2, 3, 4, 5. So we have to have 5 parts, 5 master parts that has different values, okay? And then we will do bias analysis for each part, right? That means we will get the X bar, okay? And then we will subtract X bar, okay, with reference values or master value, okay? And then we will get what we call bias, right? And then we will plot the bias, okay, as the y-axis, okay? And we will take the reference value as the x-axis, okay? And then we will get this plot bias over reference values, okay? And then we will fix a regression equation or regression line like this. In this case, the bias value spread, okay, with no pattern of linearity, okay, so the slope is pretty much like this, okay. So what we will do next is that, okay, you can take a look at this. This is what I have talked before, okay. And then you will do what we call regression analysis, or find out the best fit line. This is the equation, okay, or the line, okay. Regression equation. You have learned about regression equation before, right, in statistics course, okay. And find out the R-square value, okay. I will talk about that, okay. And then the step is that, okay, the slope of the line, okay, shows you the change in the bias, okay, when reference value changes, right, okay, the slope, okay. And if you remember R square, okay, if this is the true amount of bias, right, okay, if the true amount of the relationship between bias and reference values is, okay, like this, you can fit a line, okay, exactly, okay, on to the points, on all the points. In this case, that's mean the fit is perfect. The equation is very perfect because it can explain the data points or explain the variation of the points 100%, right? Equation is exactly equal to the actual values. That means the R square is equal to 100% in this case, okay? But in reality, the actual number may be a little bit different from the line, the numbers on the line, okay? So you will have variation, okay, compared to the fitted line. So the R square will be dropped, okay? And if the R square is still greater than 80%, okay, we have satisfying result, okay? And then we can conclude that this equation or this line, okay, relationship line can explain the variation in the actual data pretty well, okay? And then we can accept that line to be the line that represents the relationship between the bias and reference value. Okay, and the next step is that when we conclude whether the amount of linearity is acceptable, okay, we will talk about the slope. If the slope is small, okay, so what we expect is that there should be no slope, okay, no linearity. But in reality, slope may be a little bit, or like middle, or very large, like this, okay. So if the slope, for example, the slope, if you turn the slope into not as percentage. So if you take the slope and then multiply it with 100, okay, if that amount is less than 5%, you can say that you accept this amount of linearity, or you can say that the slope is not that much, okay? But if like this slope, for example, this slope is equal to 0.2, okay? When you multiply 0.2 by 100, you will get 20, right? And then if you compare 20, okay, with the criteria, suppose you accept, you use the criteria of 10%, you will say that this percent linearity is greater than the acceptable criteria. So you will say that the amount of linearity is unacceptable, okay? Or the slope is too much, okay? And if you, for example, if you conclude like that, you have to do further analysis. Okay, I will show you the result from Minitab. Okay, like this. Okay, remember how do I do the analysis, so that in the workshop you will repeat this process again, okay, with another data set. And at this time, okay, I will have you practice by your own, okay, but I and Pimai will guide you how to do this, okay, but mainly I would like you to do that, okay, by yourself, okay, by repeat this method that I'm talking about right now, okay. So maybe I'll ask, okay, some of you, okay, so that you will have a chance to participate right now. In this case, we have the reference value starting from 10, 15, 20, okay, up to 55, okay, and then we have 5 replication of measurements for each part. For example, part which has number of 55, you measure it first time, second time, third, fourth, 5 times, okay? And then you take an average, which is the red point here. The red point here is the average, okay? And then you will do that for all reference values, right? And so with this with this relationship, okay, what do you see from this relationship? Do you think that bias has relationship with the reference values or not? Okay. May I ask Supicha about this? Okay. Supicha, please take a look at this graph, and then do you think that bias has relationship with the reference value?
Can you repeat the question, Hajan?
Okay, look at this graph. Okay, this graph. Do you think that bias, okay, which is the y-axis here, has relationship, okay, with the reference value?
Oh, yes, because like at a smaller number, the bias is smaller.
Yes, very good. Okay, and then the next point is that, okay, so if we want to find out this relationship or quantify it as an equation, okay, this equation will take this form, right? Y equal to a constant, right, plus a slope, and then times the reference value. Is that right? And y in this case is the bias, right? So we will need to quantify constant and slope of this line. And the constant will be, okay, for example, do you see the black line here? This is called the fitted line or regression line, okay? And then this line, okay, you have learned before, okay, it tries to pass, okay, pass all through all the data points as much as possible, right? Okay, and then if, okay, the constant is at this point, okay, at this point, right? So it's the point that the line, okay, cross with the y-axis, right? And then we get this much slope, okay? So we will use what we call regression analysis to find out the numbers for the constant and slope. And that equation is here. The coefficient, okay, column, okay. So in this case, okay, Napakorn, could you please tell me the regression equation? So bias is equal to
minus 0.159
okay, good,
and plus 0.0109
okay,
reference value.
okay, and then multiply by the reference values, right? Okay, so this is this equation, the fitted line equation. Okay, good. And then if you have learned about regression analysis before, okay, before you believe in this line, you have to check first whether the constant and the slope term is statistically significant. So if it's significant, so you will trust in this equation. But if it's not, okay, if these two terms are not significant, you will say that this line is not significant, okay, it does not really exist, okay. So that means you have to take a look at the p-value of these two terms, okay. And in this case, p-value is like it shows that it's 0.000, okay. So may I ask Parit, could you please summarize, okay, whether do you believe that slope is statistically significant or not by looking at which numbers?
ขอแล้วคำถามอีกทีนะครับอาจารย์
Okay, my question is, okay, now we want to test whether the slope, okay, this slope term, okay, is significantly different from 0 or not, okay, or is really significant in terms of statistics or not, okay. So we have to take a look at the p-value number, okay. I'll guide you that you have to take a look at this number. And in this case, it shows that the p-value for slope is equal to 0.000, okay. Actually, I do not want to cross it, okay, 0.000. Okay, so from this information, how do you link it to the conclusion whether the slope is significant or not?
The p-value is less than the alpha.
Yeah, what is your best estimate for the p-value? Is it exactly at 0? Okay, I will repeat this one more time. Okay, in this case, it shows that p-value is this number. Is that right? Okay, but here you have to know that Minitab, okay, report only 3 decimal places. Okay, so the fourth digit here, okay, fourth digit here, it doesn't show. Okay, so but that means sorry. That means the fourth digit is less than 5. I'm not sure what happened. It disappeared. Okay, come back. That means the fourth digit here is less than 5. Okay, so you say that this amount of p-value means that the actual p-value is less than 0.0005. Okay, and then you will compare it with alpha, which is 0.05, right? And then you will say that this p-value is less than alpha, right? So Parik, again, what is your conclusion about the slope? Is it significant? Is significantly different from 0 or not?
Significant different ครับ
Yeah, okay, good. It's significantly different, okay? And you can see by line here, right? It's not zero, sorry, zero, but it has some significant number, okay? And it shows pretty much strong relationship, okay, by eyes. You can observe that, okay? So up to this point, you can say that the slope is significant. That means there is a significant linear relationship between bias and reference values. Okay. And the next step, okay, you have to check, you have to take a look at the output below here. Okay. And you will see that it will report the amount of bias, okay, at each reference values. In this case, there's limit, Minitab has limited space, okay? So it doesn't show the reference value of 45, 50, and 55. Actually, we have data point up to 55, right? Okay, but, okay, it can show, okay, because of limited space here, it can show only from 10 to 40. And then it report the bias, okay, for each reference values. And then you will see that this number, okay, the numbers of bias increase, right? When the reference values increase, right? And which is corresponding to this graph, right? Okay. And then it will turn, okay, or compare this amount of bias, okay, with the process variation. Okay, it will calculate the percentage bias. Percent here mean it compare bias with the process variation. That's mean when you use Minitab, it will ask you to enter the process variation number. Okay, in this case, okay, I have enter some number, okay, and then it will take that number, okay, and then divide, okay, take the bias and divide it by this number, and then it will calculate this column for you, okay, and then, okay, it will show you the p-value of the t-test analysis, okay. It shows the p-value to test whether the amount of bias is significantly different from 0 or not, okay. And you will see that for reference value of 10, 15, right, up to 25, okay, if you see these p-values are greater than alpha, right, alpha of 0.05, so you will say that from reference value of 10 to 25, in this case 10 to 25, okay, the amount of bias, okay, in this range, okay, is not significant, okay, it's very small, it's not significant, okay, but when the reference value is, okay, from 30, okay, 30 to 55, because it's increasing, right, to 55, so from 30 to 55, the p-value is significant, right? It's less than 0.05. Okay, so this is what you can conclude about the significance of the bias for each reference value. Okay, and when it's significant, okay, you can take a look at the percentage of the bias here. Okay, and then when you take a look, okay, at this range, you will see that, okay, come back to the criteria again, okay, if we use 5%, let's see, okay, to judge whether bias is acceptable or not, okay, if we come back to the criteria, okay, if we use 5%, that means we change this number to 5%, okay, when the amount of bias is greater than or equal to 5, okay, you will not accept, okay, but if it's less than 5, we will accept, okay, so remember this number, okay, 5% not accept, greater than 5 not accept, but less than 5 accept, okay, so come back to the output again and help me, okay, answer whether you will accept the amount of bias when the reference value is 30. Okay, do you accept that? มีใครบ้างนะเดี๋ยวอาจารย์สุ่มถามนิดนึงพี่ไมค์ค่ะช่วยเรียกน้องนิดนึงนะคะคน
ค่ะอาจาร
ใคร
ย์
ก็ได้ที่ยังไม่เรียกไป
นัดกมลค่ะ
นัดกมลไปแล้วแน่เลยใช่ป่ะนัดกมล
ยังครับ
เอายังเหรอคะขอโทษทีนัดกมล for reference values of 30 will you accept the amount of bias if you use 5% as a criteria?
accept ครับ acceptable
Yes, accept because which numbers in the exam, okay, I will ask you like which numbers that you consider when you make decision. So you have to tell me which are the numbers that you take into consideration. Okay.
Because percent bias of 30 reference is less than 5%.
Okay, so please be more specific. Okay, you can say that. Okay, you should add that because the percentage of bias at reference value of 30 is 3.2%. Okay, so you have to tell 3.2% is less than the acceptance criteria of 5%. Okay, so you will say that you will accept the amount of bias. Okay. Okay, Nakamon, one more time. For reference value of 35, do you accept that? And which numbers are you looking at?
We accept the bias because the number of percent bias is percent bias of reference number 35 is 4.3%, which is less than acceptance criteria of 5%.
Yes, very good. Okay, thank you. Okay, พี่ไมค์ค่ะขอน้องอีกคนค่ะ Now let's take a look at reference value 40. Same question, accept it or not. Okay. น้องพี่ไมค์
นรพัฒน์ค่ะ
ค่ะนรพัฒน์ค่ะ Reference value 40. What is your conclusion?
อาจารย์ครับเมื่อสักครู่เน็ตผมหลุดครับ
อ๋อเหรอคะโอเคไม่เป็นไรค่ะงั้นเราพัดลองฟังเพื่อนนะ Now we will talk about how we make decision whether we will accept the amount of bias okay for each reference value okay ในน้องไมค์ช่วยขอน้องอีกคนค่ะ
กริดค่ะ
okay great ค่ะ please conclude about reference value of 40
we accept it because the bias number is equal is 5%.
Okay. Be careful in this case. If you use 5%, okay, if it's greater than or equal to 5%, okay, you will not accept it. Okay, if it's less than 5%, you will accept it. So when it's exactly at 5%, okay, exactly as 5%, you will not accept it. Okay ไหมคะกริด
Okay ครับ
okay one more time
we do not accept it because it's greater is equal to 5%.
Okay, because the percentage of bias, you have to tell me which indicator you are looking at, right? Because the percentage of bias over process variation is exactly as 5%, which is equal to the acceptance, the criteria for making acceptance, okay, and it fall to the conclusion that we will not accept it, okay. And the last question about this, okay. if, okay, it doesn't report the numbers for a reference value of 50, right? Okay, but if we guess, okay, from the numbers that we have, okay, will you accept the amount of bias for reference value of 50? Okay, why? Okay, do you think that you will accept or do not accept it? Okay, พี่ไมค์ค่ะเชิญน้องอีกหนึ่งคนค่ะ
ค่ะศิลวิทย์ค่ะ
Silvit, could you please, okay, guess, okay, from the information that we have, will you accept the amount of bias for a reference value of 50? Silvit อยู่ไหมคะ งั้น come back to ใครนะเมื่อกี้ที่เน็ตหลุดไปอะค่ะ
ครับต้อง reject ครับ
reject why which number do
The
you
bias
consider
value is greater than 5 ครับ
why do you think it's greater than 5
because the value of bias keep increasing so if
that's
the reference average is 50 so it must be greater than 5
okay, that's good, okay, great, okay, and then you compare it with the acceptance criteria of 5%, okay, good, okay, so I think you pretty okay understand about this, okay, so we will repeat, okay, this analysis again, okay, in the workshop, okay, so I think you can do it pretty fast, okay, so we will do that, okay, after the break, okay, we'll have 15-minute breaks from now, okay, and then we'll come back, okay, please prepare your Excel file, okay, from Crossville, okay, and we will do the workshop, okay, after the break, and then I will talk about the exam, okay, the expectation of the final exam. Okay, do you have any question right now? Okay, so if not, let's meet after the break.